Okay, so this course we're gonna discuss the cyclic loading with the we say the fatigue stress, which is not completely reversible stress. Okay, so previously we introduced some SN diagram, right? So which can be used to predict the endurance limits, and we still need to consider different marine factors, right? For evaluating the endurance limits. Okay, and then we can plot the SN diagram, right? So for this SN diagram, the stress and the number of cycles diagram is based on the cycle loading, which is the completely reversible stress. Okay, so for this course, we are gonna uh, think of if there's a pre-stress, the preload existed. So what's the stress condition should be, okay? And also, if this is simple with some stress concentration, how do we evaluate its fatigue life, okay? Okay, so the fatigue stress concentration vector. Okay, so where does stress concentration comes from? It should come from some geometric change, right? Based on the design required, right? So this component need to be designed fillet, or it need to be designed a pinhole, or it need to be designed with the V-shaped groove. And those geometric change causes the stress concentration. Okay, stress concentration under cyclic loading or cyclic stress. Okay, so there's the parameters called the notch sensitivity. Okay, so which is a parameter to evaluate its stress concentration vector. Okay, so for the stress concentration under stack loading, so we already introduced that, right? So the stress concentration factor for static loading uh presented by the KT, right? KT or the KTS. This S means the shear, Okay, and for the dynamic loading or cyclic loading, fatigue loading, we use the KF, right? F means the fatigue. KFS means shear fatigue. Okay, and usually the KT is greater than the KF, and the KTS is greater than the KFS. Okay, FS. Okay, so you can think of this way: if this components or parts, machine parts, with the different shape design, and this shape design under this kind of cyclic loading, rotating, right? So you can imagine where's the stress concentration should be, right? Okay, so we can define the fatigue stress concentration vector equals to the fatigue strength of notch free. That's mean it's a perfect shape specimen divided by the fatigue strength of the notch specimen. Okay, so the maximum stress equals to, we can define it as the maximum stress, which is equals to the Kf, the fatigue stress concentration vector, times the nominal stress. Okay, similarly, the maximum shear stress equals to the Kfs times the nominal shear stress. Okay, so for example, the component with the the a groove, okay, the groove under the cyclic loading, and this cyclic loading as for the actual loading, right? So it may as the cyclic loading tension and compression. right? And the stress must concentrated around this, we'll say the notch area here, much initiated. This crack must be initiated at those, dimension change area. That means the stress should concentrate at that dimension change region. Okay, the crack will start to create it, and the crack will start to propagate. Okay, so let's say the high stress concentration area is just right at this crack form. Okay, and this crack will start to propagate and propagate and propagate. Crack grows. Okay. And the average stress is acting to the volume of the material close to the notch, right? Close to the notch. Okay, so as I mentioned previously, the notch sensitivity define the component's fatigue behavior. And the definition of the notch sensitivity Q equals to the KF, the fatigue stress concentration vector minus 1 over the stress concentration vector, the static factor minus 1. Okay. As similarly as Q means the S means shear. Okay. Fatigue shear. Okay. Fatigue shear vector. A static shear vector. Okay. Okay, so the ratio between the KF to the 100% equals to the percentage increase in fatigue stresses. Okay, the percentage increase in fatigue stresses. Similarly, the ratio between the KT to 100% equals to the percentage increase in the static stresses. So one presents the fatigue and the static. Okay. And then we can rearrange this notch sensitivity, right? We can just move this denominator to the left side, right? Okay. And then finally, we get a relation between the KF, KT, and Q. Similarly, the KFS, QS, and the KTS. So the notch sensitivity, we can say it's the parameter to convert the stress concentration under static loading to these to that under the fatigue loading. Okay. Okay, so this notch sensitivity with respect to this we say the radius of the notch has been plotted in a chart, many charts, numerous of charts, okay, to evaluate the notch sensitivity. Okay, for the evaluate the notch sensitivity, we can just use the chart to figure out to approximate the the value of the Q or QS. Okay. Okay, so let's see this chart is for the notch radius versus the notch sensitivity, right? And each curve represents different material, okay, different materials, right? Different materials corresponding to its ultimate tensile stress, the ultimate tensile stress. Okay, so it's so the left figure presents the Q versus the notch radius. The left figure represents the QS with respect to the notch radius. Okay. Okay. Okay, so for the low cycle fatigue, okay, so we can use the KF and the KFS. We can still use that to evaluate its fatigue behavior. Okay, so I'm gonna show you some example later. Okay. Okay, so the life of the parts. Life of the parts. How many cycles till failure? Okay, so this is the beam, right? The shaft under the uh the uh the the point load. Okay, under the point load. Okay, so it's like we apply constant force and release and remove the 500 Newton and we apply 500 Newton and release it. Okay, so it's a cyclic loading, right? So we apply a loading and remove it, apply it, remove it, apply it, and remove. Okay. Okay, so this shaft, two shafts, made of the machined 1035 cold draw steel. Therefore, its ultimate tensile stress equals to 550 megapascal. Okay. Okay, so the question is asking the number of cycles until failure. And as we know, the stress, the nominal stress equals to uh, the function of number of cycle, right? Function of number of cycle. SF represents the fracture strength. Okay, fracture strength. So if you still remember the SN diagram, we need the F parameter to evaluate the, let's say, the inflection point, right? So it's a parameter times the ultimate tensile stress representing the reflecting point at the SN diagram, right? The SN diagram. So we can just evaluate it by its ultimate tensile stress, 550 Newton. So while at this F factor approximately 0.875 something. Okay, so it just approximate number. Okay, so for the F value is the 0.785, right? So the 0.785 times 550, we get the 481. So it's a reflection point right here, right? So that's the start point of the high cycle region, right? Start point at the high cycle region, right? And SE prime equals to the 0.5 times the ultimate tensile stress equals 275 megapascal, okay, which is the endurance limit. Endurance limits with the perfect shape of the rotating sample. Okay, so in the practical fatigue spaceman, the SE has to be take into account with different marine factors. Okay. Okay, so we have those numbers, right? So what we have to find, well, what are those marine vectors? Ka, Kb, and the Kc. Okay. So for the Ka is the surface vector. This shaft made up by machine, right? Machining. Okay, so we can find. Okay, so machine. Well, it's about machine, right? Right here, machine spaceman. Okay. So for the SI units, we got the vector A equals to 3.04. The exponent B equals to minus 0.217. So plug this two number into this equation, we got the Ka, the value of the Ka. And the Kb is the size vector, and the diameter equals to the 15 millimeter, right? So we can plot this number to the size vectors equation, right? So we can find the KB value. Okay, and in this case, the KC, the loading vector, the shafts are subjecting to the bending, right? So we have the center force apply and release, apply and release. Therefore, the shafts are subjecting to the pure bending, the pure bending. Okay. So the Kc equals to 1. Okay, Kc equal to 1. Okay. And then we'll just substitute those marine vectors to figure out what is the SE is, right? So it's plugging those, the Kc equal to 1, Kb equals to the 0.928, Ka equals to 0.773. We plug this 3 marine vector into this endurance limits, the practical endurance limits equation, right? So we got the SE, the endurance limit equal to 197.3. Okay, therefore got the endurance limit right here, 197. So we already find the starting point, right, of the high cycle and the endurance limit, right? So this for the high cycle, high end, and left of it is for the low end. Okay. Okay, so by using the equilibrium equation, we find the reaction, right, at each bearing, and we can find the normal stress due to bending. Right, we can find the normal stress due to bending, and then we can plot this shear and the bending moment diagram. Okay, we can plot the shear bending moment diagram. Okay, so where's the shear the stress concentrated region is? Should be at point B, right? Because we have the geometric change, the fillet. So it's a point B, right? So we can just plot it. So sorry. Point B here, right? So here is the maximum stress of the maximum stress, or say the highest stress concentrated at point B. At point B. Okay. Okay, so the stress, normal stress at the point D, where's the point load applied, right? From this shear the bending moment diagram, you can find the stress, the normal stress under bending is. Okay. Therefore, the stress, the normal stress at point D, what equals to the 8.35 the megapascal. Okay, and stress at point B, okay, equals to the Kf times the nominal stress. Okay, the Kf times the nominal stress. How to find the Kf? We'll find the Kf. Also, we can find the moment from the shear and bending moment diagram, right? We can find the moment at point D and at the moment at point B, right? So next, how to find the KF, the fatigue factor, the fatigue stress concentration factor. As what I say, the KF, we say the notch sensitivity, which is a parameter to convert this stress concentration factor under static to the stress concentration factor under fatigue, right? Okay. So the first thing we have to find what is the KT is, the stress concentration factor under static loading. Okay, under static loading. Okay, so similarly we can check the table or chart. Okay, so for the questions, we find the shape with the shaft, which is the same as what we ask, right? So for the ratio between the diameter, the capital D divided by the lowercase d equals to 3, right? So we have to find some parameters to define which curve we're going to use it, right? So the capital D divided by the lowercase d equals to 3. So we find which curve we're going to use it. The top one, right? The top one. Okay, the top one. And what's the radius? So the questions already tells us, right? So it's 1.12 should be, right? Let me double check. Oh yes, 1.125 millimeter. Okay, so 1.125 millimeter right here. Right, and we'll use the top curve and the 1.125 radius. And then we can find the approximate the KT vector, the stress concentration vector under static loading, right? So it's about psi, I don't know what's the number, should be 1.8 with 2.0 something. Okay. Okay, so the KT is around 2, right? 2.0, and the similar approach to find the notch sensitivity Q with respect to the notch radius, right? Which is 1.125. 1.125. Okay, 1.125 millimeter right here. Right here. Right? And which curve we're gonna use it? Just steel, right? So so which curve we're gonna use it? We already find the radius, right? And the ultimate tensile stress is the 550 megapar, right? So it should be, the curve of the notch sensitivity with the with the ultimate tensile stress 550 megapar should be within these two curves, right? So for this curve, whose the SUT, the ultimate tensile stress, equal to the 700 megapar, and for the lower curve, right? So whose the ultimate tensile stress is the 500 megapar. Therefore, say the 550 megapar, the curve of the sensitivity, the notch sensitivity should be between, right? So between these two curves, somewhere between them, right? Okay, so we can approximately to find the Q value, which is about, say, the 0.72. Okay, 0.72. Okay, so now we have the KT and we have the Q vector. And what can we get next? The KF, right? So the KF equal to 1 plus the Q times the KT minus 1. So we can figure out the KT vector equals to 1.72. Okay, and we can plug this number 1.72 right into this equation here, and we get a KB, the stress at the location B under bending. Okay, under bending. Okay, so the sigma B equal to 260 megapound, 260 megapound. Okay. Okay, so the question asks, what's the number of failure? So the stress is a function. It's a function of the number of cycle, right? So the stress means the fatigue stress. Okay, the fatigue stress. And we already derived this SN diagram, right, from the previous course. Okay, so we'll find this curve between the high cycle, the starting point of the high cycle, and the endurance limit, right? Endurance limit. So, which is the linear equation. Okay, so we can define the number of cycle equals to sigma divided by a the power of the 1 over b, right? So use the A and B equations that we already find last course, right? A and B. So we can find the A value and the B value. Okay, and we plug the A and the B into this equation. Right? And the sigma we already got is 260 megapar, right? And right, and then we can plug those A and B values to find the number of cycle till failure under the point load applied is 170,760 cycles. Okay, so if this shaft, so it's shafted like this, right? It's the filler is subjecting to the point load. So you apply it and remove, reply and remove, reply and remove. Also, in this case, it is the completely reversible stress, right? Therefore, can use the SN diagram to evaluate the number of cycle till failure. Okay, so if this shaft is subjecting to the constant stress 260 megapar, as this cycle reach this this number, okay, when this intercept right at this linear relation, okay, this linear function. So we can say, okay, so the number of failure is the 116,760 cycles. So as this shaft, you are under the point load and release, point load and release, point load and release. When this cycle reach this number, this shaft will fail. Okay. Okay, so as I mentioned previously, this case is the completely reversed stress, sigma AR. So what's the definition of the sigma AR is? That is the mean stress equals to 0 and the maximum stress equals to the absolute value of the minimum stress. Okay, so what I say till now, we are only consider the completely reverse loading. Okay, so suppose this cyclic loading, or say the fractional stress, with a preload. With a preload. In this case, we cannot use the SN diagram to predict its, life cycle. Okay. So right now we have to consider the stress situation, that is the components with a preload applied to it. Okay, so in this case we cannot consider the completely reversible stress. Okay, we have to consider the mean stress and alternating stress by using Goodman, Morrow, Gerber, ASME, and the elliptic. And this is the fatigue criteria, okay, by using the different fatigue criteria. Okay, so for example, we have we have a spring, and we apply a preload on it. That's mean we just press it. Okay, and then we just press button, just press to the end, and let it go. However, when we let it go, the preload still existed. The preload still exists, and then we press again, and then we let it go. During the cycle, the preload is always existed. So for the stress curve, we have the preload, right, which is not zero. So we just apply the force and release preload, right? Let it go and press button and let it go, and so on. See, we always have the the preload existing. Okay, so the one example is the valve spring. Okay, the valve spring. Okay, so which is aware of the preload existing. And the other example is we say the retractable pen, right? So like a ball pen with the push button, right? So we can just click it. And there's a pre-stress always existing. So it's a fluctuating stress. And in this case, the mean stress, which is not equal to zero. Right? So in this case, that's mean the mean stress equal to zero, right? The mean stress right here equal to zero. However, for the fluctuating stress, that's mean the preload existed. So the mean stress is not equals to zero. Okay, it's not equals to zero. Okay. Okay, so some example like this, or is a trumpet, right? It's a trumpet with the button with the spring. Okay, with the spring. And when we install this button, the cylinder, right? Let's push it, press it, and the spring. This is the original dimension, right? This is the original length of the spring. And after installing the bottom cylinder, right? And this spring will be compressive. This spring will be compressive with a preload. With a preload. And if you just trumpet musician, you just push the button, right? No matter how you push and release, how you push and release the button, the preload is always existing, right? Because the spring is already reduced its length, right? Being installed inside the cylinder. Okay. And other cases like the engine, right? Right? The engine, engine cylinder with this valve spring. Okay. The difference between these two is the spring constant, right? Because they have the thick wire, and for these trumpets, the spring with the thin wire. So we're gonna introduce the mechanical component of the spring in next semester, okay, with the specific chapter to introduce the a spring. Okay. Okay, so let's look into three cases of the fluctuating stress. Okay, fluctuating stress. So the case one, so the sigma A is the fluctuating stress. And we have the minimum stress, right? We have the minimum stress. And the sigma n, which is not zero. Okay, which is not zero. Okay, the sigma n, the mean stress, is not equal to zero, and the sigma A is the alternating stress. And the second case is that the sigma n equals to zero. Okay, the sigma n equals to zero, and the maximum stress equals to sigma A. Okay, equals sigma A. And the first case that the maximum stress equals to two times of the mean stress. Two times of the mean stress. Okay, the same, the maximum stress still equals to the sigma A. However, for the first case that the maximum stress equals to the two times of the mean stress. Okay. Okay, so the third case is that the maximum stress and the minimum stress, maximum and minimum stress is doubled. Okay, it's doubled. Okay, and the minimum stress equals to the maximum and minimum stress equal to the two times of the absolute value of the applied stress. Okay, of the sigma. Okay, so what's the criteria we're going to use? So I think you should remember the SN diagram, right? The SN diagram, which can be used the completely reverse stress, right? However, for this fluctuating stress, the SN diagram is useless. Okay, so we're going to use this here. Okay, it's useless. Okay, so now we have to focus on the fluctuating stress. Okay, so we plot the figure of the sigma A, the alternating stress with respect to the mean stress. Okay, and then we can do tons of the experiments. Okay, we can do tons of the experiments to figure out the fluctuating stress diagram. Okay. Okay, so for the experiment, we can find, okay, the endurance limit, right? The endurance limit for one specific materials and the SUT, right? Which is the materials property. Right? And then we can get the different the sigma A, right? Sigma A is the alternating stress from previous curve, right? That's sigma A. Okay, so sigma A. Okay, so we can find the induced limits by experiment, right? So we can collect those data points, induced limits versus the ultimate tensile stress. Okay, and we can plot the different fluctuating stress diagram with the alternating stress and the mean stress. Okay, so when this sigma A, the alternating stress equals to zero, the sigma equals to constant equals to the mean stress. when the y equals to 0, the y equals to 0, and the x equals to the sigma n, the mean stress, the mean stress. Therefore, we can define a very conservative the region to design for this fluctuating component. So we can just connect the endurance limit to the ultimate tensile stress, right? So we say any component, say the fluctuating component, the fatigue component being designed within this range, it should be safe, right? Because the maximum stress is the endurance limit. Yeah, it's the endurance limit. Okay. Okay, so suppose we have the condition, the fluctuating stress condition of the components, right? So we have the mean stress and alternating stress by experiment. We got it. So we got the point B represents the fluctuating stress condition of parts or components, right? And then we extended the OB section to find the intercept of the linear line between the endurance limits and the SUT. And this intercept point A, right? So that means if the stress is beyond the point A, well, this component might fail. Okay, might fail. And then we can define the safety vector graphically as the ratio between the OA length divided by the OB length. Okay, and this curve linear relation, well, you can just do this calculation by yourself, and this linear relation that can be represented as this function. Okay, and we define the safety vector. We define the safety vector n equals to the inverse of this function, of this equation. Okay, this equation. Okay, that's the definition of the safety vector by fluctuating stress diagram. Okay, so you can think of this way. We can have the different region, right, in this fluctuating stress diagram, right? So each line with the different criteria, what I mentioned previously, the Gerber, SME, Goodman, and so on. It can be defined by you because you are the engineer. Okay, therefore the different criteria with the different equation for safety vectors. Okay, for safety vectors. Okay. So any questions for that? Okay, so this is one example. The fatigue criteria by the fluctuating stress diagram from the different engineer or different method, Guman, Moran, the Sonberg. Okay, so for the Guman, which define the line between the endurance limits and the SUT, that's the ultimate tensile stress, and for the moral criteria, which is define the linear line between the endurance limits to the true stress, true fracture stress. Okay, true fracture stress. And for the Soderberg, we define the fatigue criteria between the SE, the induced limit, and the SY, the yielding stress. Okay, the yielding stress. Okay, so what is the S sigma F, which is the fracture true stress. Okay, the true stress, the true stress for fracture. Okay. Okay, so well, just tells you the different uh criteria from the fatigue criteria for the fluctuating stress diagram. Okay, because those figures are made by terms of experimental data. Okay, so for what we already know is the Goodman, Morrow, and Somber, right? For the different line, and there are other criteria like Gerber, right? Which is a parabolic curve, and the SME ellipse, and the SW and Walker. Okay, the different curve, different fluctuating stress curve. Okay, so we can just use the different criteria to find the safety vector under the fluctuating stress. Okay, okay. Okay, so the course I'm gonna stop ended here, and next course I will just present some examples by using those criteria, Goodman, Morrow, Sonberg, Gerber, and so on. Okay, okay, so the course will start here.